In this next section, we're going to look at measures of variation. Two data sets can have the same mean, the same middle, but have very different distributions of values. One might have a distribution where most of the data values are clustered around the mean, while the other has data values spread out to either side of the mean. So what we're looking at here is just how spread out the data is. So first off, range equals the difference between the minimum data value and the maximum data value. And then we have standard deviation, which is the term that we're going to be using the most. It is the average deviation, the average difference of data values from the mean. And the equation looks like this, where this is the data value, that's the mean. You take the difference, you square it, you divide by 1 less than the total number of data values, square root the whole thing, and that gives you your standard deviation. We use the letter S for standard deviation of a sample. There is another equation that is often used. It's called a shortcut formula. Basically, we have the sum of the squares, subtract the square of the sum, and then divided by n times n minus 1, and again square rooted to give us the standard deviation. If it is a population, we use sigma here. This is very similar to the e's that we were looking at before, but this is lowercase Greek letter for sigma. And the difference being, instead of x bar, we're using mu because now it's population, and instead of dividing by n minus 1, n is the size of the population. So very similar equations, these two, but one for a sample and one for a population. Now the variance is basically S squared, or sigma squared for population. So really the variance, which is a measure of the variation of data values, it's the same equation. It just take away the square root part and you've got the variance. The values of this S squared tend to center around sigma squared, which makes S squared an unbiased estimator of the population. So that means that, generally speaking, S squared gives us a pretty good approximation of sigma squared. Unfortunately, we can't say the same thing about S and sigma because of that square root. We have what's called the rule of thumb for many data sets, which are fairly normal. 95% of the data lies within 2 standard deviations from the mean. This allows for an estimation of the minimum and maximum data values by knowing the mean and the standard deviation. The minimum value is approximately the mean subtract 2 times the standard deviation, while the maximum is approximately the mean plus 2 times the standard deviation. Furthermore, we can use the range to approximate what the standard deviation would be. Standard deviation equals approximately the range divided by 4. Now, whereas the rule of thumb says that 95% of the data lies within 2 standard deviations of the mean, we also have what's called the empirical rule. So let me push that up just a bit. And in the empirical rule, for a bell-shaped, so in this case we are specifically talking about a bell-shaped distribution, about 68% of the data falls within 1 standard deviation of the mean, 95% falls within 2 standard deviations of the mean, and 99.7% of all the values fall within 3 standard deviations of the mean. And you can see here the dark blue here, that would be 34 on each side, so together 68.2, and then you've got another 13.6 in the lighter blue, and then the very light just 2.1 that falls within 3 standard deviations between the 2 and the 3 standard deviations. So a rule that sometimes makes it helpful for us to estimate things. We have Chebyshev's theorem, which for any distribution the proportion of data values lying within k standard deviations of the mean is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. I just included that for completeness, but I'm not really going to test you on that particular thing. Now, if you have a frequency distribution and you want to find out its standard deviation, it's very similar, but again, here we have x minus x bar squared, so there's your difference between the data value and the mean, and f. F is the frequency for each class, and again, x would be the midpoint of that class, and then divided by n minus 1. And then finally, we finish up with coefficient of variation, CV. It is a way that allows you to make comparisons between different data sets that are not necessarily at all alike, but basically what you're doing is saying what the relative variation is between the two data sets, because you are comparing their standard deviation to their mean in both cases. So these are the highlights of section 4. Let's look at some examples now. First off, we're going to look at a couple of examples of finding the range, the standard deviation, and the variance of a couple of data sets. So first off, the range, again, it's the max, subtract the min. So here the highest was 13, subtract 6, you get a range of 7. Over here, the high was 27, low was 1. So again, you subtract and you get 26. Now, mean, of course, I can't do standard deviation without having the mean, because the standard deviation is the basically average distance from the mean of all the data values, so I need the mean. So if I add these up, there are 5 of them. 50 divided by 5 gives me 10. Likewise, on these ones, if I add them all up, they also give me 50 divided by 5 is 10. So part of what I did here is give you 2 examples in which the means are exactly the same, but they're going to have very different standard deviations. So it can sometimes help. You don't have to do it this way, but it can help to kind of keep things organized. So what I've done here is, this is x, so these same values, 12, 6, 13, 11, and 8, 12, 6, 13. And then what I'm showing you is their differences from the mean. So 12 subtract 10, that gives you 2. 6 subtract 10, that's negative 4. 13 subtract 10, that's 3. 11 subtract 10, that's 1. And 8 subtract 10, that's negative 2. So this entire row here are the differences of each data value from the mean. Then we square those data values. So 2 squared is 4, negative 4 squared is 16, 3 squared is 9, 1 squared is just 1, negative 2 squared is 4. Then we add them up. Again, the little sigma symbol here, it looks like a kind of E. That stands for sum. So we have just summed all of these squares. That got us to 34. The actual equation now is the square root of the sum of those squares divided by n minus 1. There were 5 values, so our n minus 1 will be 4. 34 over 4, and then square root gives me an average, gives me a standard deviation of 2.915. Now, if I want the variance, it's just the 2.915 squared. However, you're better off just taking what was inside the square root, in this case 34 divided by 4, which gives me exactly 8.5. You're more likely to come out with the right answer that way, instead of taking this, which you may have rounded, and then squaring it, and you might have then been off of the 8.5 just a little bit. So, here's our second case, and again, these both had means of 10, but now my values are 5, 27, 2, 1, and 15. Our mean is 10. So 5 minus 10, negative 5. 27 minus 10, 17. 2 subtract 10, negative 8. 1 subtract 10, negative 9. 15 subtract 10 is 5. And so here are all the differences from the mean. Now we square them. So now we have nothing but positive numbers after we square. add up all these squares. We got to 484. So this time it's 484 divided by 4, because again there were 5 values, so 1 less than 5 is 4. 484 divided by 4 is 121. Square root of 121 is 11, so our standard deviation is 11. And then here, 11 squared, or 484 divided by 4, our variance is 121. So basically, in the first data set, we had a standard deviation of about 2.9. Here we have a standard deviation of 11. They both had the same mean. But what's going on is this data set had a lot more variation, a lot bigger standard deviation than this data set. So this one was much more clustered together than this one was. And that's the value of standard deviation and variance. All right. Now we're going to move on and look at our rule of thumb. Use the rule of thumb to estimate the following values. What are the maximum and minimum values if the mean is 30 and the standard deviation is 6? And so the maximum is x bar plus, so that's the mean plus 2 times the standard deviation. So 30 plus 12 gives me 42. The minimum is x bar, the mean, subtract 2 times the standard deviation, so x bar minus 2s, 30 minus 12 gives me 18. Now, again, this is the rule of thumb, so really what we're getting at is between 18 and 42, 95% of the data values should lie. It's an approximation, but approximately 95% of the data should lie between the values 18 and 42 if they have a mean of 30 and a standard deviation of 6. In this next one, we're going to go in the opposite direction and go, okay, find the standard deviation if I know what the range is. Well, in that second set that we had, we went, the low was 1, the high was 27, so there's our range, 26, 27 minus 1. And again, it's always divided by 4 because we're thinking, again, 95% of the data is 2 standard deviations above the mean and 2 standard deviations below the mean, so 2 and 2, that's 4. And so the formula is range divided by 4, and so in this case the standard deviation would be 6.5. Now you might note that the actual standard deviation was 11 when we did this particular data set, whereas this came out. So this is just an estimation and really will be dependent on just how many data values you have. Alright, so now we're going to use the empirical rule to make some estimates of how much of the data would be 95% or 99%, given that the mean is 50 and the standard deviation is 5. So remember, with the 95% rule, it's plus or minus 2 standard deviations from the mean. So 50 plus 2 times 5 plus or minus 2 times 5 means that 95% of the data will be between 40 and 60. And of course, this is for bell-shaped type data sets. On the other hand, 99% rule, it's 3 standard deviations on either side of the mean. So 3 times 5, 15. 50 plus or minus 15 means that 99% of the data should be between 35 and 65. And then one last example using the coefficient of variation. Again, the coefficient of variation for samples is the standard deviation divided by the mean times 100. And so we're going to look at comparing men's heights to their weights. And as you can see, the means are very different, the standard deviations are very different, but this gives us a way of comparing them. So first for the heights, 3 divided by the 68 times 100 gives us about 4.4%. Over here for the weights, 26 divided by 173 times 100 gives me about 15%. So what we can say in making a comparison here is that there's a lot more variation in the weights than there is in the heights of these people who were in the sample. And so, measures of variation.